Lesson 5, Bias Circuits. Section 5.2. Stability Factor. The results of experiment 5.1 showed that the circuit in A was robust to temperature changes induced by hot air. On the other hand, the circuit in B, which did not have RE, was highly sensitive to temperature changes. At high temperature, the circuit lost its ability to amplify the input signal. The main cause of this instability is the transistor's sensitivity to temperature changes. This graph shows an example of how the IBVBE characteristic varies with temperature. The red line represents the case at ambient temperature equals 25 degrees Celsius, and the blue line represents TA equals 30 degrees Celsius. This is an example of the IC-IB characteristic affected by the ambient temperature. If IB is kept constant, VBE decreases with increasing temperature. In the case of the IC-IB relationship, IC increases with increasing temperature. This means that HFE increases with increasing temperature. Furthermore, transistors, even those with the same model number, such as 2N3904, have individual differences. For practical use, the bias circuit must be designed to be robust against not only temperature changes, but also unit-to-unit parameter differences. Let's quantify the stabilities of these bias circuits. Subsection 5.2.1. Robust bias circuit. According to Thevenin's theorem, the circuit containing R1 and R2 can be transformed into the equivalent circuit shown in the right figure. This transformation simplifies the analysis of the circuit. Exercise 5.2.1. This is your homework. Pause the video, and answer the problem. Let's analyze the stability of bias circuit by using this equivalent circuit. DC voltages and currents are denoted as in this figure. Along the loop 1, Kirchhoff's voltage law gives this equation. According to equation 3.1, IE equals IB plus IC. This is equation 3.3. HFE is the DC current gain. Along loop 2, KVL gives this relationship. The target of this stability analysis is to find delta VCG. To achieve this, we first need to determine delta IC. From equations 1, 2, and 3, IC is expressed with this equation. The stability factors of a transistor are defined as these partial differential coefficients at the operating point Q. These factors are the derivatives of IC, with respect to HFE, VBE, and ICBO respectively. A first-order approximation of the total change in ICQ is given by this equation, where delta HFEQ, delta VBEQ, and delta ICBOQ are variations at the operating point Q, due to temperature changes and unit-to-unit parameter differences. The third term is related to the reverse current through the reverse biased junction. According to the data sheet of the 2N3904, the typical value of this current is 0.3 nanoamps. This term contributes little to delta ICQ, so let's neglect it. By partially differentiating IC in equation 6 with respect to HFE and VBE, we obtain these expressions for SH and SV. These are the values of the designed bias circuit at the operating point Q. The stability factors SH and SV are then calculated. The variation delta ICQ is calculated by using the derived stability factors. Delta HFEQ is the variation of HFEQ. It is given by CHQ times HFEQ times delta T, where CHQ is the variation ratio HFEQ with respect to temperature. Its unit is 1 per degree Celsius. Delta T is the temperature difference. Delta VBEQ is the variation of VBEQ. It equals CVQ times delta T, where CVQ is the variation ratio of VBEQ with respect to temperature. Its unit is millivolt per degree Celsius. Approximate values of CHQ and CVQ are 0.005 per a degree Celsius and -2.0 millivolts per a degree Celsius respectively. Assuming a temperature rise of 40 degrees Celsius, then delta ICQ is approximately 83 microamps. From equation 5, delta VCG equals -RL delta IC. So, the variation delta VCG equals -RL delta ICQ, and it is calculated as -0.27 volts. In experiment 5.1, the DC component VCG was approximately 3 volts before the heating. After the heating, VCG became approximately 2.6 volts. Thus the variation delta VCG was about -0.4 volts. The calculated result and the experimental result agreed fairly well. Exercise 5.2.2. This is your homework. Pause the video, and answer the problem. Subsection 5.2.2. Non-robust bias circuit. This is the non-robust bias circuit. It does not include the resistor Re. The current I1 and the base current IB flow through these paths. I1 should be equal to or greater than 10 times IBQ. So, I1 plus IBQ should be equal to or greater than 32 microamps. In this circuit, the base emitter voltage VBE is equal to the base ground voltage VBG. Then, R1 should be equal to or less than 136 kilo-ohms. Let's select 51 kilo-ohms for R1. Thus, R2 is calculated as 8.03 kilo-ohms. Thevenin's theorem gives the equivalent circuit in the right figure. DC voltages and currents are denoted as in this figure. Exercise 5.2.3. This is your homework. Pause the video and answer the problem. The values of SH and SV are found. The absolute values are larger than those of robust bias circuit. The variation ratios CHQ and CVQ, as well as the temperature difference delta T, are the same as those in the case of the robust bias circuit. Then the current change delta ICQ is calculated as 2.6 milliamps. This value is very large compared to 83 microamps of the robust bias circuit. Along the loop 2, according to KVL, VCG equals VCC minus RLIC, and thus delta VCG equals -RL delta ICQ. Delta VCG is found to be -8.6 volts. With VCC equals 5 volts, VCG becomes negative in this equation. However, in the actual circuit, VCG cannot be negative. This means that the amplifier become non-functional. Note that delta VCG was -0.27 volts for the robust bias circuit. These are the waveforms of VCG and VBE for the non-robust bias circuit. The left figure shows the case before the heating, and the right one shows after the heating. VCG dropped from 3 volts to 0.2 volts. VCG reached its minimum value after the heating. The author of this material is Takeshi Furuhashi, Professor Emeritus, Nagoya University. If you have any questions, send emails to this address.